Okay, welcome everyone to the 2020 APAC Groundbreakers virtual tour by APAC UC. This year, our event will be the biggest one ever done with 174 sessions, including normal sessions, workshops, and hands-on labs from 123 different speakers over 11 days. Also, it will cover sessions on 4 different languages. And please remember to register to as many sessions you can, and all sessions will be available to replay as many times you want for 2 weeks after the initial session date and time. You can also interact with the speaker at any time during that 2 weeks by posting questions or comments directly on the playback session page. I would like to say thanks to our Oracle user groups and Java user groups that made this event possible, and also to our sponsors, Oracle Groundbreakers and CloudDB. Now for today's session, Optimizer Statistics, the Key to Efficient Scalable Databases and Applications by Richard Foote. Please feel free to write questions at any time during this session using the Q&A tab, and Richard will respond on his convenience. If he don't want to see during this session, I can read for him all the questions at the end. It's up to him. But if you have any issues happening, any technical issues, please let me know using the chat option. In other words, any questions to Richard, please use the Q&A option in the Zoom webinar. If any technical questions to the moderator, in that case me, Francisco, please use the chat option. Now, without any more delays, I would like to leave you with this amazing session by Richard Foote. Rich? Oops. I'm just stopping my sharing, and you can now share your screen and take control.
Alrighty, welcome everyone. Hope everyone can hear me. If you can't, scream out loud. All right, so what we're going to talk about is, and just to emphasize, we've got 90 minutes or 85 minutes. So it to me wasn't clearly stated, but just know we've got about 90 minutes to go through. We're going to discuss a whole bunch of stuff around optimizer statistics and how vital they are to the performance of your database.
Richard, I cannot see your screen yet.
You cannot see my screen?
No. Can you reshare your screen, please?
How do I reshare my screen? Because I don't.
You should have the option share again in the top. Let me see.
I don't have.
They show in the top, on the bottom where they have share screen option. Let me see if I can.
I've got a little box that says host to, but it's got nothing on it other than exit.
Okay, now let me see right here. They should be able to show the same screen that before to you to share. Let me get here, Richard. Let me see. And let me see. You should have a share screen option. That's strange. I will also make you a host, and let's see if that allows you to see better.
Okay.
Okay, I'm making you the host now at the moment. There we go. See if you can see the option to share screen now.
I can see them. No, all I've got is a little square that says H on it, and I can't make that any.
If you go to the screen up, you should see more options to the menu. You go to the cursor to the top up center of your screen. Or if you go the tab option to go using a Windows or a Mac?
I'm using Windows.
Windows, if you go the top option to change it to applications and you go back to the Zoom application, they should show you all the options of the menu, because you should have many options.
Okay, so I've just increased that. Hit share screen. Hold on, that's come up. Can you see me now? See me now?
Yes. Now I can see your full screen with the bolts in the back, and now the presentation.
Beautiful.
And not in presentation mode. Now in presentation mode. Now
all good?
It's perfect. Apologies with that.
That's all right. All good. So so for anyone that doesn't know me, this is basically my life in one overhead. I guess the two most important things is that I've been working in IT probably a little bit too long now. I don't increment these numbers, although I'm not that far away from incrementing the first numbers in each of these, but I may retire before I get to that point. And the other key thing that, for those who don't know me, is I'm a mad David Bowie fan. So you may find there's going to be the odd reference or two to the great man as we go through. A lot of information that I discuss you can find on my blog or will be put on my blog. So if you're not aware of my blog, visit it. There's lots of good stuff on there. Alrighty, so what we're going to talk about is Oracle and the optimizer and statistics in particular. And this is a huge topic. Like literally, I could spend days talking about it. And in fact, I've actually got a 2-day seminar where I actually spent a great part of those 2 days just talking about how the optimizer works and the importance of statistics. All I'm going to do today in our little 90-minute session is start by looking at how the CBO uses some key optimizer stats, so we understand how the optimizers use the stats and why they're so important. Then we're going to look at some common issues and traps around statistics. And I'm going to focus mainly when they're actually up to date. So yes, you can have all sorts of stats when they're wrong and not captured and so on. But my focus is that you're actually doing best practice. You're actually collecting stats as one would normally do. And we're going to discuss some of the issues that you can still encounter. And then I'm finally going to talk about a bunch of newer features where Oracle's always trying to make life easier for us. So we're going to look at some features where Oracle will automatically collect stats when it thinks it's necessary, different level statistics, missing statistics, gather things more frequently, and we'll look at that. And it's important to understand that because we need to understand why our queries suddenly change for the better or for the worse, and understand some of these things that happens behind the covers. All right, so stats collection. I'm going to assume everyone knows how you collect stats. You should be using DMM stats package. That's the way we've been doing it for yonks. Oracle does have a maintenance window, and part of its maintenance window, there is a stats gathering job. So if you do nothing, you just install a database every evening, by default between 2 and 4 in the morning, there will be a stats job that will be working for 2 hours, collecting what stats it thinks it's necessary. In later versions of Oracle, if you're on Exadata, you'll find that this stats gathering can happen much more frequently. And there's what's called real-time statistics as well, which I'll touch on later. But I guess the key thing is, as a DBA or as a developer, we want to make sure that we do collect stats and we make sure that we collect them appropriately, which is generally speaking is with DBMS stats package. Now, in terms of the stats that get captured, there's a whole bunch of stats that we can view. The ones I'm going to focus on today, the key important ones are rows, the number of rows, because obviously it's important for the optimizer to know how many rows there are in a table, and also the number of blocks there are in a table. So they're your 2 key stats. Now, there's a whole bunch of others that also can get collected depending on how you collect your statistics, but they're the 2 that I'm going to be focused on today. Regarding columns, there's again a whole bunch of different types of column statistics, but the 3 crucial ones are the number of distinct columns. So how many different values do I have for a particular column? That gives the CBO some idea on the percentage of rows it might expect, depending on how many of those values you're after. And also the low and the maximum range of those columns. So what's the minimum value and what's the maximum value? And there's a whole bunch of other ones which also get covered, but they're the key ones that we're going to be focused on today. From a purpose of indexes, again, a whole bunch of stats to get covered when you cover statistics, but the key ones we're going to focus on is the B level, which is effectively how many IOs do I need to navigate so that I start at the top of my index structure and get down to the bottom of my index structure, where all my leaves are. How much work does the CBO have to do that? Then there's the number of actual leaf blocks inside my indexes. So how wide is my index? And if I want to get 1% of my rows, I need to use 1% of my index, then I need to know how many leaf blocks that's likely I'm going to have to access. And another key statistics, which we'll touch on later, is the number of distinct keys for an index. And the optimizer can use that in a myriad of ways. And most importantly, and for anyone that's ever attended any of my talks, I can't do a talk without mentioning the clustering factor. It was by far the most critical of all the statistics that I've discussed is the clustering factor, which indicates how well ordered is the data in my table, which could be effectively potentially be in any order in relation to my index. And the index must always be stored in the order of my indexed columns. So the question is, how well clustered, how well ordered is my data versus my index? So what I'm going to do, I'm going to start with a very simple example, and I'll go through this with other presentations. I'm just going to touch on it here. So what I've got here is I've got a table. I've got my good old Bowie table. Told you there's going to be a few references, and I've got these two key columns, code and grade. Now, when I populate this table, the data for code will be nicely ordered. So I'm going to insert all my ones and then all my twos and all my threes for my code column. And there'll be 100 distinct values for code. But grade is going to get populated via a random generator. So it's going to generate a number between 0 and 100, and it will just pick them randomly. So the ordering of my grade column will be nowhere near as tightly coupled as my code column is. I collect my statistics. We'll discuss these various options in a tick, but just going to collect general statistics, and we're going to create an index on both of those columns. So like I said, the key thing is initially table, what's the stats on my table? I've got 496 blocks and I've got 100,000 rows in my table. Okay. Here is my statistics for my index on my code column. And we can see that it's a B level 1, which means I've got to just read one block before I get down to my leaf blocks. I've got 195 leaf blocks. I've got 100,000 rows in my index. Same as my table means I don't have any nulls in my index. I've got 100 distinct keys. We know this. There's 100 different values. But note that the clustering factor is really low. And by really low, what I'm saying here is that the number 490 is much closer aligned to the number of blocks than it is to the number of index entries. So what that's telling me is that my data is very, very well ordered. I'm going to, inside my table, I've got all my ones together, all my twos together, all my threes together. Why? Because my clustering factor is tiny. And my minimum and maximum values are 1 and 100. Great. So now I'm going to run my nice simple query. And out of a 100,000 row table, I'm only going to get 1,000 rows. So the selectivity is reasonably small. And most people would think, yeah, an index would probably be where they go to get just 1,000 rows out of a 100,000 row table. Now, key thing I want to mention, I'm going to say the keyword key because there's a whole bunch of key things I want you to note. Key thing number 1 to note, that if an optimizer gets the selectivity correct, or in this case, the correct term should be the cardinality, it's getting the right number of rows, it's estimated right number of rows. It's 1,000 rows been returned. Yes, 1,000 rows says the optimizer. Then we can have some confidence that the optimizer is doing the right thing. Because by getting the correct cardinality, as we'll see, it means it's got the correct selectivity. It's getting the right percentage of rows. And if it gets the right selectivity, it means that it's using the correct formula behind the scenes with the correct numbers. What we see here is the cost of using this is 7. 2 for using the index, and it goes up by 5 when it comes to accessing the table. So what I want to quickly go through is where do these numbers come from? So the first thing and the most critical thing of all is we've got to get the selectivity correct. We've got to get the right estimate, the right guess for the number of rows. So what Oracle's saying here is we've got 100 distinct values. I only want one of them where it equals 42. So that means I'm going to get 1% of my data. So I'm using what's called the density of 0.01. Now, if I multiply 1% by my number of rows in my table, again, remember this is a statistic, Oracle's estimating that I'm getting 1,000 rows. So that is where this number comes from, and it's absolutely correct, which means it's got this percentage absolutely correct. And this percentage is critical because it gets used in this formula. So this is a very famous formula about how Oracle costs an index. So the cost of using an index is we need to read the B level. We're going to go down to our leaf page. So the number of B levels we've got to get to. Then we've got to read X percentage of the index. In this case, it's 1% because I want 1% of the data. So I need to read 1% of my index. So it's 1% of the number of leaf blocks. Then I've got to go and visit the table. So this is where the clustering factor becomes so critical, because what the clustering factor effectively says is how expensive is it for me to read the entire table through the index. The default in this example is 490 because that's my clustering factor. But I don't want to read the entire table through the index. I only want to read 1% of the table. So therefore, the cost is the B level. Now, because the B level is less than 2 or equal to 2 or less, Oracle ignores what's called the root block. The first block we forget about. So effectively, it's 1 minus 1, which equals 0. Then we add the cost of using the index. It's 1% of the 195 leaf blocks. That equals 2. So this is where this number 2 comes from. It's 2 blocks, says Oracle, roughly of the index we need to read. Then, well, how many table blocks do we need to access? It's 1% of the clustering factor. 1% of the clustering factor gets rounded up to 5. 5 plus 2 equals 7. And that's where these numbers come from, 7. And because these numbers are accurate, I'm confident it's doing the right thing. What I'm going to do, I'm going to run exactly the same query, but using the other column. So this is the column where I don't have such good clustering. Same number of rows being returned. But in this example, there's 2 key differences. Difference number 1 is the cost is much, much higher. All right? It's not 7, it's 137. And 2, it's not using the index, it's doing the full table scan. So instinctively, we know that the index, which I do have an index on this, the cost must be greater than 137, because if it was less than 137, it would have used the index. But it's not, it's 137. So now what we need to work out is where does that 137 comes from? So this is where I introduce you to system stats. Now, system stats gets used by full table scans and index scans and and all other types of parts. So the system stats is vital for that, but it's particularly vital for our full table scans. So what system stats tell us is it gives us the Oracle the indication how fast our different types of IOs are, how fast our CPUs are, and what is the average size or the expected size of our multi-block reads, because these are all key things to consider when we start looking at the cost of the full table scan. So there's a big debate in the Oracle world whether you should gather no workload or workload stats. I'm not going to touch on that here, but just note, modern versions of the database use the system stats. You need to be aware what your system stats are. You can investigate it in this view. So in my particular example, I have used workload stats, and I've got a read, an S read time, which is my single block read time is 2 milliseconds. My multi-block read time, the time it takes for Oracle to read multi-blocks at a time on average, is 10 milliseconds. My CPU speed is approximately 1,120 instructions per second. And the size on average in my database for multi-block read, meaning how many blocks do I read every time I do a multi-block read, is 20. Now, how do we cost a full table scan? Well, effectively, a full table scan is the number of table blocks divided by the multi-block read count. That tells us how many actual multi-block reads we take. And if I know then how fast my multi-block reads are, I can then calculate how long it takes to do my multi-block reads. Now, what Oracle also does is it calculates, well, how many CPU cycles am I expecting to do to expend when doing this amount of work. So it calculates internally how much work is required and then divides that by, well, how many CPU instructions can you perform per second, depending on the speed of your CPUs. Then what Oracle does is it takes this total time, the total IO and the total CPU time, and divides it by the time it takes to do a single read so that the measurement we use is single read blocks. So how do we determine this cost of 137, of which 9% was CPU? You just do this. You say, well, for a start, there's no single block reads. Well, actually, there might be one when we read the header, but we're going to ignore that. Fundamentally, we just do the number of multi-block reads, which is 496 divided by 20. That gives me the number of my multi-block reads, because that's my multi-block read count. And then I multiply that by the time it takes to do a multi-block read, which is 10 milliseconds. So 20 multi-block reads into my 496 blocks gives me X number of multi-block reads, multiplied by 10, gets rounded to approximately 250 milliseconds. That's how long it takes to do all the multi-block reads to read my table, 250 milliseconds. But what Oracle does, it divides that figure by the time it takes to do a single block read. So I convert this time into units of, well, how many single block reads equivalents is that? It's 125. So the cost of reading this table is effectively 125 single block reads, however long that would normally take. The cost, though, is 137. And the reason is because 9% of that cost is CPU, because Oracle needs to calculate, well, how much CPU do I need to burn? So reverse engineered 9% of 137 is approximately 12. So 12 units is CPU, 125 units is IO. The total cost is 137 for my full table scan. Now, like I said, the full table scan is winning, which means I know my index is losing. I know my index is slower. So the question now is, how slow? Why slower? So one of the nice things about using things like a hint to force Oracle one way is I can now investigate, well, what would have been the cost of using the index? So by running this query using the index, the cost was $390. 390 is greater than 137. That's why the full table scan won. So the question is, where do these numbers come from? Why 390? Note that the cost of the index is still the same. It's 2, just as it was previously, but it's much more expensive, says Oracle, to get the data out of the table. And the reason why comes back to the clustering factor. The clustering factor for the code for the grade column is terrible, because I've been inserting that in a random order inside my table. And because I've got a terrible clustering factor, when I use my formula, which is still 1%, it's still only 1% of my index. So the index cost is the same. Where the jump in cost explodes, it's 1% of my awful clustering factor. And 1% of this equals 387, which gives me a total IO cost of 389. Now, we add 1% because if you go back, there's about a 1% overhead for IO. So we add about 1, we round it up for 1 more for IO, and that's where our 390 comes from. 390 is just too damn expensive. So in this example, it's not that the stats are wrong, it's just the stats are saying clearly it's too expensive to use the index. The index is not the efficient way to get the data. So if it's just purely, I've got a really badly clustered data, but this query on grade is absolutely super critical, I can't afford to do a full table scan, I need this to be much, much quicker, then one option I've got is I can change the clustering of my data in my table. I can add a clustering attribute, say I want this to be clustered by grade. I can now do an online reorg of my table, and now I can improve dramatically the clustering factor of my code column, because now the data is clustered by grade inside my table. Note, by the way, by fixing this, I've now stuffed up the code clustering. But maybe from a business perspective, I'm happy to do that. I run this grade query all the time, super critical. The other, not so important. So now when I run my query again using the grade column, hey presto, much more efficient. I'm not doing thousands and tens of thousands consistent gets. I'm using my index really efficiently, because all the data that it needs to fetch out of the table are all grouped in a very, very small number of rows, because my data is literally clustered so well now. Okay, so the difference is, again, was just the clustering factor. I'm getting the performance I was getting for code, because now the clustering factor for grade has been dramatically improved. And of course, if you start playing around with the clustering of the data, just know you can fix one, but you can hurt somewhere else. Now it's my code column query that is suffering, but maybe that's a choice I want to make. One point I will say, it is actually possible to cluster both properly. Why? Because the cardinality of both is so relatively small. I'm going to get this only in distinct values that I could potentially subcluster one within the other and get good clustering for both beyond the scope of this. Now, Reason why I focus on the clustering factor so much is that in most databases, for most columns, even when the columns are well clustered, you're going to get a terrible clustering factor. And my little experiment I use for that is I create my little table here. I've got my ID, and I'm simply got a procedure that just inserts 100,000 rows, and I'm just using a sequence, an ordered sequence, to insert 1, 2, 3, etc. into my table. So in theory, my data should be very well clustered for ID. But importantly, I'm going to execute this procedure from 3 different sessions, which means session 1 inserts into some blocks, session 2 inserts into different blocks. Why? Because ASSM is designed to avoid contention. I don't want multiple sessions to be inserted into the same block. So the beauty of ASSM table spaces is that it helps to avoid contention. The problem, though, is my 3 sessions are all inserting their rows into subtly different blocks, which means they're not going to be perfectly ordered in my table, which means if I look at my clustering factor, after I run this, even though the data is pretty clustered, like most of the data is pretty close to each other from an ordering point of view, the way the clustering factor is calculated by default says if the previous entry is not the same block that I'm visiting now, and I have to visit a different block when reading my index, I increment the clustering factor. Even if the block's right next to the one I've just visited before, even though I may have visited that block just a couple of blocks ago, the default is if I keep changing the block I need to visit, I keep incrementing the clustering factor. So in this example, even though in a 300,000 row table, I only want a few hundred rows, it's too expensive to use the index, only for a few hundred rows, because I have to visit things Oracle because of my terrible clustering factor, too many different blocks. So key thing, and I can't talk about stats unless I mention this, since 12, although it's been backported to 11, you should be looking at table cache blocks as a mechanism to fix up your clustering factors. These will fix the clustering factors where your data is actually quite well grouped, but Oracle doesn't think so. The default value for this is still 1. And I would recommend setting it to 16 because 16 mimics the behavior of the free list-like behavior of ASSM. Bugger 16, I'm going to use my favorite number 42 because 42 is a magical, mystical number. And what happens now is when I say 42, what happens is if I visit one of the last blocks, one of the last 42 blocks that I've visited, I will not increment the clustering factor, which means I could have a whole bunch of blocks right next to each other, all being accessed, and I come and visit them again and again. But if it's one of the last 42 blocks that I've visited, then hey presto, don't increment the clustering factor. And the result is now I have a tiny clustering factor. And what I would like to say here is it's actually a much more accurate clustering factor. This was artificially incremented because the calculation was just all wrong. Here I'm doing much more, it's making much more sense. If it's one of the last few, don't worry about incrementing the clustering factor. And now when I run the same query, 2 key points. 1, it uses the index automatically. And 2, the cost is tiny. Why? Because now to read these 300 odd rows, they all live effectively in the same set of blocks, says Oracle. So I can actually absolutely read an index very efficiently because the clustering factor is now much more accurate. And the big warning, and this is still true in the current version of 19C, still true in the autonomous databases or on 19C, is that if you rebuild an index, when you rebuild an index, it recalculates the statistics. And when it recalculates statistics, it does not use table cache blocks. So you've got to be really careful every time you rebuild indexes to recalculate your statistics again. Otherwise, you're going to be in a world of pain. I've been told it's going to get fixed soon. I haven't tested this with 20C. Not many people have, but it still is an issue in 19. Okay, now that we've looked at a non-equality query, let's just quickly go through the costing of it. And fundamentally, what Oracle does is exactly the same thing. It needs to calculate, well, what percentage of rows do I need to visit? And whatever that percentage of rows is, it uses that inside its formulas. So here I've got a query where I want to get everything where the code is greater than 10, but less than or equal to 25. And Oracle says, well, the cost is 106. Remember, the cost of the full table scan is 137. So anything under 137, the index will win. And here it's winning. We read in few enough rows for us to access the index. So where did these numbers come from? Okay, note, by the way, the numbers are close, not perfect, but pretty close. 16,000, 15,000, it's in the right ballpark. So the first thing that Oracle always got to do is calculate the selectivity. So this is why the number of distinct values and the minimum and the maximum are so critical, because I always got to work out, well, what percentage of the rows is this? So this represents, well, how many numbers are there? It's 25 minus 10, so about 15 values. Well, how many values are there in total? Well, the maximum is 100, my minimum is 1, so Oracle says there's 99 different values. Note, by the way, instantly we got a rounding error, because there's actually 100 distinct values, but Oracle's deeming it to be 99. So this is where these rounding errors can come in, and sometimes in edge cases it can be problematic. So that's the percentage of rows that we need to access. It's basically 15 divided by 99. But because we've got an equality predicate on one side of the condition, because we say, and we want equal to 25, we also add the selectivity of one value for each equal sign that we've got. The selectivity of this, because we've got 100 distinct values, is 0.01. So the total cost of this is 0.15 recurring, which is 15 divided by 99, plus the 0.01 for the equal sign, which gives us a selectivity of 0.1615 recurring. So that is when we multiply that by the 100,000 rows, that's where this number of rows is coming from. And it's in the right ballpark. And if that's in the right ballpark, that means this figure's in the right ballpark. And this figure's in the right ballpark, it means when we use it inside our formula, it's this percentage of leaf blocks, it's this percentage of the clustering factor. We're confident that the cost will also be roughly in the same ballpark. So just note that this percentage of 195 plus the 1 for the B level, it's not an equality predicate, so we're going to include the B level this time, equals 33. But the cost of the index access was 35. So 33 is IO, but 6% is CPU. 6% of 35 is roughly 2. So that's where we get the 35. 32 of it's IO, 2 is CPU. That's where we get the cost of 35. So if I go back, that's where this cost of 35 comes from, 6% of which is CPU. If we look at the cost of the table access, it's 70. 70 plus 35 gets us up to 105. But note the cost in total is 106, of which 3% is CPU. We already worked out where 2 of that comes from. It comes from the index, which means we've got the missing 1 is the IO required for us to do the accesses to the table, says Oracle. So that gives us our cost of 106. 106 less than 137, that's why Oracle uses the index. Now, a problem that we can get yourselves into is when we start querying data that is beyond the known threshold of data. Now, my maximum grade is 100, and I'm saying I want where it's 150. Now, no rows have been selected, right? With no rows, we should be using an index to get me the fact there's no rows. But Oracle's not. Oracle's doing the full table scan. Why? Because Oracle's not guessing 0 rows. Oracle's estimating 495. And it's just too expensive to get 495 rows through this expensive index with the poor clustering. So where does this 495 come from? So what happens is this. When we start querying data that is beyond the known values of our data, Oracle uses a sliding scale by which the further out we are from our known value, the less I'm going to reduce the estimated selectivity of that query. Now, my known range of values, my maximum is 100, my minimum is 1, so I've got 99 values, says Oracle, and I'm 50 over the maximum. So therefore, I'm going to reduce the selectivity of one value by 50 over 99. So that's how I'm going to reduce that selectivity. It doesn't become 0. I'm saying I'm going to reduce it by 50 over 99th, which means I'm going to assume I'm going to get 0.4949 recurring of the one selectivity, because there could maybe be data that is outside the known boundary, because who's to say my stats are up to date? Who's to say I collected stats yesterday, but I have got some data that's outside my range? So this is why Oracle does this. Now, selectivity of 1, remember, is 0.01. If I multiply that by my reduction, it's going to be 0.004949 recurring. I multiply that by that, and that's where my 495 estimate comes from. But this percentage is too great. If I put that into my clustering factor, it thinks it's going to be too expensive, and that's why Oracle is not using the index. If I go way, way out, so past the known range by the width of my total range of values, then eventually I get to the point where Oracle thinks I'm only going to get 1 row. So when I say greater than 200, Oracle says you only get 1 row. If you only get 1 row, then yeah, absolutely, an index would be a great way to get 1 row. And the difference here is because my total range of values is 99, and because I'm 100 over that, I'm past that threshold, which means I'm going to reduce selectivity down to just 1 row. And 1 row is just 1/100th of the data. And for that, I will absolutely use my index. So these minimum and maximum boundaries are critical to the optimizer because it bases a lot of its calculations based on that. Now, one myth I want to get rid of right now is that if you've got a stable environment, everything works perfect, all your queries are perfect, don't touch anything. Don't leave your stats alone, because if everything works perfect, you leave your stats alone and therefore nothing can break. It's when you collect stats that you're going to maybe stuff things up. But that's not true. All right. So that is not a viable strategy. You've got things working, never touch anything ever again. And to illustrate that, I've got my table here where I've got my Ziggy date. And I'm going to insert a whole many years worth of data. So 1,830 days worth of data gets inserted, and I'm just inserting this into my table. I collect my statistics. Great. Now what I'm saying is I just want 1 year's worth of data. So this is my sys date. Take away 365. Give me anything that is up to 365 days ago. And Oracle's saying, well, that's going to be about 360,000 rows. And that is way, way too expensive to use an index, which is great. I actually want to do a full table scan. This is too great a percentage of my data, a year's worth of data. I do not want to use an index to do this. Now, if I don't collect stats for a year, what happens is my data changes. I will now insert a new year's worth of data. So this is what I'm doing here. I'm inserting another year's worth of data into the future. And I'm not going to collect stats because everything's fine. So what I'm doing now, I'm going to run this query as equivalent to what it would be like in a year's time. In a year's time, the sys date will be 365 days later. And I want the previous 365 days. Now, what's happened, as I mentioned before, is I'm now gone past my boundary of known data. And if I go too far past my boundary, I'm reducing my selectivity. I think I'm getting less and less and less data. And eventually, I'm down here. Oracle thinks I'm only going to get 951 rows because I'm so past my date, because I've not collected statistics now for a year. And now it's using an index incorrectly to get me 10 to 1,000 rows of data. All right. So the fix here is to keep your stats up to date. Keep your stats up to date. Keep your stats up to date. We know what our minimum maximums are. And now we correctly and accurately, I'm only out by a little bit. And now the optimizer's doing the right thing. So simply not collecting stats is not a viable strategy. All right. Now, what I want to talk about now is data skew. So when we talk about statistics and Oracle getting things wrong, one of the key ways it gets things wrong is because it's not picking up data skew properly. Or maybe it is, but we don't have quite the right stats to actually get us all the way there. So what I'm going to do now, I'm going to create a table, and I'm going to populate it with lots and lots of 20s initially, and then I'm just going to update whole bunches of rows. So there's going to be a whole bunch of rows that have got a value of 18, 1,000 are going to have a value 2, 5,004, and so on and so on. Just note some of my values, 12, 14, 16, they're only going to have 100 rows. So some of my codes are very popular, and some of my codes are not very popular at all. So I'm going to create an index on code, but just note I've got my data everywhere. All right. So if I'm after value 12, there's only 100 rows. And to get 100 rows out of a 1,000,000 row table, maybe an index is the way to go. But if I'm after value 20 and that's more than half my table, well, maybe that's not the way to, maybe I should do a full table scan. So I've got data skew here. All right. Now, key point to make with this is that if you collect your stats by default, and I ordinarily would recommend you do this, so just let method opt for all rows size auto, let Oracle decide whether or not how to collect the statistics and whether or not, importantly, to collect a histogram. Now, when I run this normal stat collection, I don't have any histograms. Why? Because I've not yet run a query that has used a column in this table that has data skew. Why bother collecting histogram information on a column that I don't query? So Oracle doesn't do that. I need to have both data skew and I need to have used that column somewhere. So this is the problem for all these new queries that I might introduce into my database, queries that use columns that have never been used before in predicates, because they may not have the necessary statistics for them to work properly. So just always be wary of that. So what's happening here is when I run my query with code equals 16, Oracle doesn't have anything other than the minimum, the maximum, and the number of distinct values. I have 10 distinct values. So if I want one of my 10 distinct values without any other information, it has no idea other than to assume you want 1/10 of the data. 1/10 of the data is 100,000 rows. So that's why it thinks it's going to use a selectivity of 0.1. And that's too expensive for an index. But that's not true. It's actually only 100 rows. So key point number 2 is whenever this number, reality, does not meet the CBO estimate, we can get ourselves into all sorts of problems. So one of the key things you always want to look out for when you got a bad plan is the optimizer getting this wrong? Is it getting its estimates wrong? Because very commonly, it's where it gets its estimates wrong is where the query goes wrong. Now, here I've got a hole in my data. I've only got 2, 4, 6, 8. So there is actually no value 7. And 7 is within my range. So again, it's getting things hopelessly wrong. It thinks it's getting 100,000 rows because 7 is within my minimum and my maximum range. There's nothing for it to think. Why wouldn't there be 7s? The stats would suggest you're going to get 100,000 rows. If you ever have this scenario where you've got a query, it's problematic, you're not entirely sure what to do, this is where something like gather plan statistics is really useful. Now here it's bleeding obvious, but sometimes when you've got these plans that go for pages after pages, what you're looking for is what part of the plan does my estimate not match my actuals? And that's often where you need to focus. I've got a point in my plan where Oracle's estimating 100,000 rows, but in actual fact, he's only retrieving 100. So clearly, I've got some deficiencies in my optimizer stats at this point, which introduces now to histograms. So histograms is where we can give Oracle additional information so it can identify data skew. Because by default, if all we know is the minimum, the maximum, and the distinct number of values, there's nothing there to indicate data skew. So this is why we have histograms. And there are 4 basically types of histograms. We've got frequency, height balance, top frequency, and hybrids. Now, I want to go through each of them very quickly because you need to understand not only that you may or may not have a histogram, but what type of histogram is being used, because that can actually determine also some of its calculations, which can maybe cause problems as well. So very quickly, frequency histograms. I describe them as the most preferable because you're going to get the most accurate data out of this. So what a frequency histogram says is I have enough distinct values that I can determine the selectivity of each value pretty well perfectly, assuming my stats are up to date. But this will only be possible by default for those columns that have less than or equal to 254 distinct values, because I can only keep 254 buckets worth of data by default when I calculate my statistics. I can actually use less than that manually, and note from 12C, I can actually now manually say more than that, up to 2K worth of buckets, but the default behavior is for up to 254. So in this case, I've got 5 distinct values, which means for each of my 5 values, I know precisely how many rows I've got of each. And if I know how many rows I've got of each, and I know the number of total rows, I can calculate the selectivity perfectly for each and every value. However, if my number of distinct values is greater than the number of buckets that I have available, then I can't do that. I can't create a bucket for each. So the default value, unless you use Oracle's default calculations, is to have height balanced histograms. So what Oracle says is for each bucket, I'm going to fill roughly with the same number of rows in each bucket. So here I've got 4 buckets. So I'm going to fill each one with roughly the same number of rows. And for each bucket, I will know the minimum, the maximum, and also the number of distinct values for each of my 4 buckets. Now, by default with height balance, if I've got a very popular value, it means that it could be in more than one bucket. So what I can see here is 42 must be a pretty common value because it appears in all my 4 buckets. So if I've got 4 buckets and I say, and I'm going to collect statistics, and I've got more than 100 values, then height balance is the way Oracle will go. Okay, so now what I'm going to do is this. If I want where code equals 42, Oracle goes, well, where is 42 in my histogram? I've got 2 full buckets full of 42s. This bucket and this bucket's got nothing but 42. So that means at least 50% of my data is 42s. However, this one also contains 42s, but here it's just, and assume that I've got values all the way through to 100. That means I've got 42 distinct values. That means 1/42th of this bucket is also made of 42s. So I've got 0.5 plus 1/42 gives me my selectivity. Here, I've also got another bucket that's got a 42. Here, I've got, say, 58 distinct values, of which one of them is a 42. That means 1/58th of this bucket is made also of 42s. So if I add 142 plus 0.25 plus 0.25 plus 58 over 100, 58, 1/58, that gives me the selectivity of 42. It's quite high. It's over 50%, meaning I'm probably going to do a full table scan. But if I just want the value 10, 10 only resides in this bucket where I've got the values up to 1 to 42. So 10 represents 1/42th of this bucket, and I've got 4 of them. So that's 1/42th of a quarter. And that becomes now my selectivity. 1/42th of 1/4 is actually quite small. So maybe I'm going to use an index for that. But you can see how it's not necessarily perfect. I might actually have a hell of a lot of 10s. Most of this data could be 10s, but Oracle's going to treat it as only being 1/42th because I could only get the information that there is within a given bucket. Now, to fix some of the limitations of height balanced, Oracle with 12 onwards has introduced 2 slightly better, more flexible, gives us better range of data. So the first one is top frequency. So what top frequency does is this. If I've got more than values than the number of buckets, so I can't use frequency because that's my favorite, frequency is my favorite, but I can't do that because I've got more than a number of buckets. However, if the majority of my rows would live inside the number of buckets, so the number of actual common values is by vast majority would live within those buckets, then why bother having stats for all the really less frequently known values? If they're really, really low and very, not many of them, then what I can do is I'll just have a histogram on those most common values, get really accurate values for that, and anything else where there can't be many of them, so who cares? I'm just going to default those to being very, very rare. So the benefit now is for those columns that do have lots of values, and I want to make sure that they're nice and accurate. This gives me the mechanism to do that. And where they're really, really rare, I'm not going to capture that, and I don't care because they're really, really rare. The last one, which again you get if you just let Oracle decide the selectivity or how much sampling to do, is what's called a hybrid histogram. So a hybrid histogram, I don't meet all the previous 2 criteria, which is frequency, I've got more than the number of buckets of values, and 2, they're actually quite split around a bit. So the vast majority of the values wouldn't reside inside my buckets. So what Oracle does, it's like height balanced. So it's similar to height balance, but it will not allow a particular value to spill over into multiple buckets, because that kind of wastes my buckets. So what I'm going to do now is I'm going to keep a count of the last value. How frequent was that last value? So that way I've kind of get the best of both worlds. I've got height balanced in that I've got that, but for the really common ones, which would be the end values, because that's what would cause them to spill over, I will know the frequency of my end values. And that's why it's kind of a little bit of the best of the both worlds. And we need to understand, A, we need histograms, and B, which one Oracle's come up with, because that can figure into our costings. I'm just going to take a sip. Alrighty. Now, what I've got here is I've got no histograms at the moment. So I can create manually histograms. I can say opt column size 42. I want 42 buckets, please. Now, there's only 10 distinct values, which means I can fit my 10 values into 42. So it doesn't matter I've got extra buckets. They just don't get used. So because I've got less values than buckets, I'm getting a frequency histogram. And DBA tab histograms is where I can get my useful statistics on histograms. So here what I can see is these are my values. These are my inputs. And because the numbers are kind of match up, it's a little bit with the raw values. If you look at dates and characters that you have to sort of be able to convert that. But here we can see that the value 2 has got 10,000 values. The number 4 has got 5,000 because it's 5,000 past that. Number 6 has got 1,000 values and so on and so on. So this is a frequency histogram. And now that I've got my frequency histogram, when I say we're code equals 16, brilliant, 100 rows, perfect. It's got that estimate perfect, which means it's correctly now using the index. Where I say code equal 20, it's a known value. There's heaps of them. So because there's 654,000, bugger the index, I'm going to do the full table scan. That's much cheaper. To use the index would be far too expensive. Now, this is where it gets a little bit interesting. If I have a hole in my data, that's also a form of data skew. So what Oracle does is this. The code number 7 doesn't actually exist, but it is within my min max range. So what Oracle says is I'm going to look at my histogram. What is the lowest value I've got? The lowest value I've got is 100. I've got a value somewhere where it's 100. So I'm now going to treat this to be 50% the lowest value, 50. So I'm going to, if it's a value I don't have, but it's within my min and max range, I'm going to use 50% of the lowest contained histogram that I've got. And that's why it says 50. And ordinarily, that's not too bad, all right? Even though it's not spot on, it's a lowish number because it's the lowest I've got in my histogram. And so it will do the same thing as by half of my lowest value. So just note there's a column called density, which gives us this selectivity, okay? And it's one that gets calculated and it gets impacted if you collect histograms. But just note that it's not one that the optimizer ordinarily use. It actually calculates its density on the fly. It's useful information for us because it tells us that if we are after a value that is not one of the columns in my frequency histogram, then the selectivity is going to be extremely low. And the default value that Oracle uses for this is 1 divided by 2 times the number of rows in my table. But this number is more for information. It's not necessarily the number the optimizer itself uses. So what I'm going to do, I'm going to insert a few more rows. And the value 3 is brand new. Okay, so I've never had a 3 before, so I've got 4 values of this. All right, I'm now going to create my histogram. Okay, I've used this column in the past. So with auto, remember, I've got data skew and I've used this column in the past. So Oracle will now create my histogram for me. And I can see that it says you've only got 4 rows. So one of the subtle differences now is that previously, when I ran something that didn't exist, it was 50. Now, because I've got a new value that's much less, okay, it's using half of that. So you can see now it's only thinking it's 2 rows. Previously, it was 50. Now, what I'm going to do is I'm going to create a table that has actually no real need for histograms because every single value has the same number of rows. Each of them got 100,000. But what I'm going to do is I'm going to run a query that runs a value which is a whole within my min and max range. Now, 8 exists. 8 spot on, 100,000, 100,000. It's one of my known values. This will be spot on. but 9 doesn't exist. So by default, what does it do? It picks the lowest value. Okay, and my lowest value is 100,000, and 100,000 is no good. Okay, now at the moment I don't have a histogram. All right, so it's got no choice. It has no knowledge of this whole. So I'm going to create a histogram. But the problem I've got is that when this one works the same, histogram's fine, but for this one, where I don't have the value, half of the minimum is 50,000, and 50,000 is too expensive because I've got lots of values or lots of commonality for all my values, and looking for a hole within my data, frequency histograms ain't doing it for me, because the default behavior of using just half the lowest estimate is still too high. And this can occur. You can have times when you're looking for values that don't exist, or they can exist, but they don't exist when you collect the statistics. They can come and go during the day, but at night when you collect the stats, it's not there, they're not there. So if you run into these sort of issues, sometimes what you need to do is you need to create some dummy records. So you want to be careful with this. You don't want to make a mistake that is identified as a real record. But what I'm going to do, I'm just going to insert a dummy record, all right? One that's got very few rows. In fact, it's only got 1 row. So now when I create my histogram, Oracle knows that I've got this dummy value, 0 only has 1 row. So now when I run my queries where I may get data that's very infrequent, data that comes and goes, now that I've got a value of 1 in my histogram, it's not going to use half. 1 is the lowest it can use, but 1 is great. 1 is perfect. All right. And so now I am getting the behavior that I want. So the key moral here is sometimes frequency histograms or histograms on their own is not enough. You need to understand sometimes the behavior around a histogram. Okay, top frequency. So what I'm doing here is I'm creating some rows. I've got 10 values that are very, very popular. And then I'm going to insert a whole bunch of more values, 250 of them, which are very unpopular. And I'm going to collect stats by default. So this is a perfect case for a top frequency histogram. Note also, when I've collected my stats, I've said buckets only 20. So I've only got 20 buckets. But because the vast majority of my rows are common and they can fit inside my 20 buckets, then Oracle uses this as a top end frequency histogram. I don't care about all my uncommon ones because they're so rare that I'm just going to treat them as if they don't exist anyway. So the behavior now is, if it's a known value, perfect, beautiful. This is very, very common, and I want this. I want to do a full table scan. All right. Slight difference behavior with top end frequency is because we don't have all the values. The default value for whole is whatever the lowest value of my top end frequency histogram is, with the exception of my minimum and maximum values, because my minimum value and my maximum value are always in a top end frequency. Okay, so just know it's a subtle difference, and this subtle difference can mean the difference between one behavior and another, because it's doubling potentially the default cardinality. Now what I'm doing here, I'm going to insert 1 row, which is 270. It's only 1 row, but because it's the top value, the maximum value, it now becomes one of my 20th values, because I always store the maximum and the minimum values, but they don't get included in my estimates for values that don't exist within my min and max range values. 265 is within my min max. It's only 1 though, so it's not enough to be one of my top end frequencies. So 265, even though there's only 1 of them, it ain't in my top frequency because it's not one of my top frequencies. It's not one of my top 20s. So it's going to default to the behavior, well, what is the minimum value? If I insert a whole bunch more of 265s, and it now becomes one of the top 20 most common values, then suddenly it will become in my histogram. And what was previously one of the least popular ones gets kicked out as a result. So now when I run this, I get perfect cardinality estimates. So just note, these cardinality estimates In most cases, they're good. They're close enough. Sometimes they can be out by enough that can cause a problem. And if you can understand this behavior, it makes deciphering and fixing these issues a lot easier. Now, a very common issue is around outliers. So what I'm going to do here is I'm going to create a table and I'm going to insert 10,000 days worth of data. And I've got 100,000 rows. All right, so I've got 10,000 days worth of data, each with 100 rows. My maximum date when I ran this was the 9th of June 20. All right, so when I say get me anything that's greater than the 9th of June 20, remembering that a date has a timestamp, which means anything past midnight gets included, here are my 100 rows. And it's perfect. There are 100 rows for that day. So no drama at all. Everything works fine. However, all you need to do to destroy this query is insert one bad value, an outlier. I'm going to insert one row and I'm going to say that the date for this is the 8th of January, 9999. Now, most of you know it's David Bowie's birthday in the year 9999, where he will still be revered and remembered, but this has stuffed up my database. Why? Because when I collect statistics, because I've never needed a histogram before, and I've just used manual statistics gathering, I've just said method op, get me size 1. Don't worry about histograms, please. I don't need it. I've never needed it before. Now all hell's broke loose. Now I'm not using an index to get me my 101 rows. I'm doing a full table scan. Why? Because now I've got an outlier, and that outlier is my new maximum value. And remember, with a range scan, what we calculate is what percentage of the data am I querying? What is that percentage over all my data? Now, because the maximum is the year 9999, I want everything that's greater than 20, Oracle thinks I'm going to return the vast majority of the table. It doesn't realize there's a massive hole between the 9th of June and the year 999. Without a histogram, there's no way for Oracle to detect that. So to fix this, there's two things I could do. One is I can create a histogram, because with having a histogram, Oracle will be able to then determine the fact that actually in my last bucket, I've got a huge hole worth of data here. Or the other thing is don't insert outlier values, all right? Be cleverer with what default values you put in there. Why have I inserted this outlier? It's to prevent the problem in the first place. But by creating a histogram, here I've got a hybrid histogram, and now Oracle is getting the selectivity spot on. It is 101 rows, and yes, the index is the way to go. Now, another form of data skew is when you have relationships between data. And maybe it's not a histogram that we need, is what's called extended stats, what we need. So what I've got here, I've got a very basic example just to illustrate this point, nice and simple. I've got 4 columns, code 1, 2, 3, and 4. And they all have 20 distinct values, but there's a relationship between these columns, meaning that actually they're all the same. Okay, so all the values are always the same in each of these data. Now, sometimes we have this, sometimes we've got relationships, and the classic case, of course, is date of birth and star sign, right? So if you're born in January, you're not going to be a Gemini. There's no such things as Geminis. There's a relationship between some of this data. Now, by default, Oracle does this. I've got 20 distinct values for each of these. So the default selectivity is, I think, if I'm going to select where this equals that and that and that and that from these 4 columns, I think it's going to be one of 160,000 values, because that's how many possible combinations that it could be. But there's actually only 20 combinations in my data. So what I'm going to do, I'm just going to create a couple of lookup tables. So that's all they are. These are just little lookup tables that I'm going to join to. I'm just going to create my foreign keys. I'm going to create my primary keys and keys, etc., etc. But importantly, the important thing I'm going to create here is an index on these 4 columns. Why? Because I'm going to run a query with selectivities on those 4 columns, predicates on those 4 columns, and I want an index on those 4 columns. And because I've got an index on those 4 columns, Oracle knows how many distinct keys you've got, because that is one of the statistics that we get. It says you've got 20 distinct keys. So even though there could be 160,000 possible keys, Oracle knows that you don't. You've only got 20 of them. So when I run this query where I want code 1 equals to this, and 2 equals to that, 3 equals to that, note we are getting perfect cardinality estimates. Oracle says, yeah, you're getting about 10% of the data. And with 10% of the data, absolutely, I want to do full table scans and hash joins, because that's how you join big voluminous amounts of data together. But note, I'm not using the index. Why? Because if I'm going to get 100,000 rows, it's too expensive to use the index to treat that much data. So what do? I drop my index, don't need it. But without the index, I lose the fact that I know there's 20 distinct values. Without that index, I have absolutely no idea what the number of distinct values is. So now I'm back, says Oracle, to guessing you're going to get 1/160th of the data. 13 is not even remotely close to 100,000. It's got this terribly wrong. And now the plans all change. It's doing a sort join. It's doing a sort because there's 13 rows, thinks Oracle. 13 rows is really cheap to sort, but it's not. It's a 100,000 row sort that you're doing. So this has gone terrible. So couple key things here. One, if you've got data where there is a relationship between the data, then maybe what you need is extended statistics, where instead of collecting stats individually on each column, I can create a collective. I want stats on column 1 and 2 and 3 and 4, please. And so Oracle creates a virtual column which says, well, for that combination of columns, there are 20 distinct values. And now that I know that, these queries will run beautifully. So that's number one. And number two is if you ever drop an index, and it's a concatenated index of more than one column, seriously consider collecting extended stats on that combination of columns, because otherwise you could fall into the trap I've just discussed. All right, SIP time. Now, the good news in some ways is there are things that Oracle does to try and help us with some of these scenarios where we're getting things wrong. So I just want to quickly go through some of these things that you may see happening behind the scenes. Now, first thing that can happen is you can have what's called cardinality feedback. So this is where Oracle learns from one execution, oh, actually, no, my guess on number of rows is totally wrong. If I'd known that, I would have done something different. So cardinality feedback is where Oracle learns from previous executions. But the problem with cardinality feedback is it's only used in limited cases. And once the query that's prompted the cardinality feedback gets aged out, I've lost that data. That data gets tied to the query. And the next time I run the query, I'm back again to not knowing the cardinality. So I get this type of scenario. So here I've got my data skew table. Just the data, I've got values all over the place. Just note 8, value 8, very few rows. I've got a couple of lookup tables because I'm going to join to this table. And I'm going to run this query where code equals 8. Now, note that because I'm doing a one query table on one column, Oracle goes, there's nothing really I can optimize on this. Seriously, if you're getting this wrong, what the hell is wrong with your stats? Because there's only one column here, all right? So this is not re-optimizable. But if I run a query such as this, where I'm joining this, doing that, I've got some complex, then this is optimizable. And if it's optimizable, then Oracle can learn from that query. So what I'm doing here is when I run this again, second time, there's different ways I can do this. Remember my gathered plan stats? I can have a look at my estimate and actuals, and I can see that Oracle is getting this spot on. Okay, so even though I haven't collected any histograms, no histograms, Oracle has learned from previous executions that actually there's 10 rows here. It's using statistics feedback. But when I flush my share pool, the thing gets aged out naturally. And then I next run this query, I'm back to think without the histogram, it thinks it's 1/10 of the data. So this is where you get these queries that run good, bad, good, bad, good, bad, good, bad, because queries getting aged in and out. So another thing that Oracle can do is what's called dynamic sampling. And dynamic sampling is where Oracle can look at the data as it passes the statement, so I can actually learn on the fly, because actually the statistics are such that I'm not confident that my estimates are being accurate. So dynamic sampling is actually being rejigged to be called dynamic statistics. And just note, since 12, there's the spinal tap level of dynamic statistics, which is 11 auto, which what Oracle will automatically, if it feels necessary, will calculate additional statistics on the fly because the statistics that it currently have are inaccurate or missing. So there's a whole bunch of different levels. I guess the two things I want to mention is by default, all things being equal, it uses 2, which means we only do dynamic stats if there are no stats. But there is a new level 11, which could be the default. We'll discuss how we can set that in a minute, where it can do this much more vigorous examination of the data on the fly. So level, basically, CBO checks for success and stats. If it's deemed inefficient because of my predicates, because of my joins, it's having to do guesses. Why guess when I can know? So it samples as it runs the thing on the fly and uses the data that it learns, caches that, and uses those statistics to hopefully generate much more better plans for us. So what I've got here is I've got 2 tables. They've got code. Both of them have got 20 distinct values. One is simply used on the mod, one's a random number. So there's actually no relationship at all between these codes, between these 2 tables. All right. And I'm just going to have dynamic sampling set at the default, which is 2. So when I run this join, I've got this typical problem I've got. Oracle knows roughly how many rows it's going to get from the selectivity on one table because it can do that, where B1 equals code 1 equals 1, you can work out roughly the number of rows. I think I'm going to get 40 here. And I think I'm going to get about 50 rows from here. But the question is, when I do the join based on the IDs of these values, well, how many rows am I going to get now? And there's no easy way for Oracle to know this. So what Oracle does by default, it just takes the lower figure and says, well, I'm going to assume I'm going to get 40 of them. It could be anything up to 40. So I'm just going to assume I'm going to get up to 40 of them. But in this case, it's hopelessly wrong. I'm actually only going to get 1. So, and because it's wrong, all hell can break loose, right? In this example, no, but you can imagine if I'm going to do subsequent joins, all hell can break loose. So if I set my database to actually have a default optimize the dynamic sampling to 11, it means that actually, no, this is a complex enough query for me to use dynamic stats of level auto 11 to actually more accurately determine the outcome of my joins. It's 1. And I'm going to use that number now to maybe, come up with a better strategy or a better plan. And I can do that at database level. I can do that at session level, and I can use a hint to say I want to do this. All right. Actually, no, for this query, I want to get this query absolutely right. So yes, I want to go to the expense of doing dynamic sampling, please, for this query. Now, another flavor of this is adaptive statistics. Now, adaptive statistics came with 12.1. In 12.1, it was deemed by default for most sites to be really expensive. So when it was a all or nothing, it became really problematic. So with 12.2, Oracle's allow, or onwards, we allow to turn adaptive stats on or off, but still have the ability to do what's called adaptive plan on and off. Adaptive plan is always nice and good. Stats is kind of expensive, and it may depend whether you want to do that. So depending on what database version you've got, there's different ways to turn this on. And the plan is this. The idea is we submit it. The CBO does the best plan on what it can, but during the execution, it goes, actually, I got this wrong, and oh, there's missing stats here, and would it be nice to have known the relationship between that data? So what it does is that it actually determines the stats based on the execution of that statement. And those stats get stored in an area where it's shareable. Other queries can use it. It's not just tied to the one SQL. And more than that, these stats can then get written permanently to disk. So not only do you keep them permanently, but if you shut down your database, restart, et cetera, you still keep these statistics. So the idea here is we get much more accurate statistics, and it's permanent. It's not this on and off type of thing that we had with cardinality feedback. So what I'm going to do, similar setup as before, I've got my data skew. Note, no histograms. I've got no histograms at all. Okay, and I want to be able to have the optimizer, please, to have this ability to determine these adaptive statistics automatically. So it could be that I've got just a whole bunch of, and I've actually have a customer that had this. They had so many bad queries that they turned this on, even in 12.2, because it actually solved more problems that it created. Yes, it comes expensive. Yes, some pastimes can be slower, but man, it means I'm getting much more accurate plans as a result. So now when I run this plan, note, I'm getting the estimate spot on, even though I don't have histograms on this column. Why? Because it's using a SQL plan directive to actually calculate on the fly that for this column group, this is the actual number of rows that I'm getting. And even if I flush my share pool or bounce my database, whatever, because I'm using a plan directive, she stays. It doesn't age out like it did previously. All right, now, now I've got to be careful here, right? If you're on Exadata, all right, I've got some good news. Or if you run on something that runs on Exadata. So now I'm thinking the autonomous databases, because the autonomous databases, their infrastructure behind the scenes is an Exadata. So with 19C on an Exadata-like platform, there are two new features that helps us with this managing of statistics. The first one is what's called real-time statistics. So what I'm going to do, I'm going to create a table. I'm going to populate with 100,000 rows, and I've got my my code column with 100 distinct values. All right. Initially, I've got no stats. For this to work, you must have statistics. So real-time statistics will not work on any table that has not had statistics gathered at some point. So you've got to gather stats at some point. All right. So I'm going to do that. Now I've got statistics. So what I'm going to do is just note, currently, I've got 100,000 rows in my data. Note that the min and max values that I've got for my two columns is it's between 1 million and 1 to 100 for code. They're my min and max values. Now, what Exadata can now do is this. When I start adding in more data into my table, Oracle on the fly will update these statistics. It will keep a tab on how many rows I've got, and it will try to keep a tab on what the current maximum or minimum values are for my individual columns without having to recalculate the statistics. That way, the stats stay valid. That way, my precious num rows, which is one of the most critical of all statistics, remains accurate. I don't have this scenario where it gets out of date and all my plans die. Here, I don't have this scenario as much where I'm going outside of my known max boundaries, and so my estimates and my calculations become problematic. So what I'm going to do, I'm just going to do a normal insert. Okay, so this is not a parallel insert. It's not a direct insert where Oracle could do some clever stuff previously. It's just a normal conventional insert. But note now, I can gather statistics as I do my insert. Dynamic stats are being used even for a conventional DML. Now, Oracle can use that information stored in cache, but if you want to see it, visualize it, have a look at it, you can flush it to disk. This is something that gets executed every, I think, 15 minutes by default, but if you want to manually do it, hey presto, we can do this manually. And we can see now we've got these augmented statistics. So now, actually, we do know there's actually 1,001,000 rows in this table. We note that the maximum is no longer 1 million. It's actually close, but not spot on. So what I want to emphasize here is that the maximum, and also this happens to minimums as well, if you were to insert new minimums, it's not necessarily spot on, all right? But it's better than being totally out of date. It depends how it gets sampled. So it's better, it's not perfect, which means you can't stake your life on that value absolutely being the maximum value, but at least it's better than it was before. And my understanding is in the future, Oracle's aiming to try and get this value spot on as well, to the point where maybe you could use it to say, what is my maximum minimum values? You're not at that point yet. But the nice thing is when I run my new query, I'm getting the correct analysis. Because remember, I need to know what is the percentage of my data. And so things like number of rows, et cetera, are all critical bits of information. Now, the other thing you can do is what's called high frequency statistics gathering. And it's turned off by default on an Exadata, but turned on by default if you were on an autonomous database. And you can control for how long the stats gathering runs for and how frequently you want it to run for. And these are in seconds. So effectively what I'm saying here is I want to turn high frequency stats on. I want it to run for 15 minutes and I want it to run every 15 minutes. So effectively, this could be running all the time in the background. Now, the reason Oracle kind of says that this is for Exadata is because we've got something that's running in the background that could be burning a lot of your CPU, and Oracle's saying, well, you know, hey, you got plenty of CPU on Exadata because they're so efficient, right? So that's kind of the logic. So I don't work for Oracle, so I don't follow that logic, but that's kind of the way it works. It only works on Exadata. So what it does is it can detect when we need to collect statistics for particular scenarios. It's not going to go through and calculate fresh stats for everything. What it does is this. It can detect where I may have a table that has no stats at all. So I've got a table with no stats. There's low-hanging fruit. I'm going to collect stats on that. I may have stale statistics. I may have statistics where I've collected stats, but I've inserted so much new data that my current statistics are now stale. And at that point, it might warrant collecting new statistics. And very nicely, I think very nicely, I've got this scenario that we've discussed already. I've got my data skew. I have no histograms. Why? Because I've never had a need for them in the past. I've never run a query on code, so I've never had to worry about it. But now what I'm doing, I'm going to run a query, and I've got this totally wrong. I've got data skew. I've got 100 rows being returned, but without the histogram, with my 10 distinct values, Oracle says, well, that's 10% of your data. That's why you're doing a full table scan. Ouch. In an Exadata, you basically have to just wait 15 minutes. All right? Because at the moment, I've got missing stats, I've got stale stats in this table, and I don't have a histogram, even though I've run a query that would have benefited of a histogram. They're all the prompts that I need. I'll wait for my, however long you've set it for, 50 minutes later, and hey presto, my table that had no stats now has stats. My table that had stale stats now has up-to-date statistics. And when I had a query that would have loved a histogram, if only I had one, now I've got it because Oracle's detected that I've got column usage and data skew, and a histogram would be very nice. So now when I run this query, it just does it behind the scenes, okay? It's now got this cardinality estimate spot on. And if I had an index, it would have used index. I just don't happen to have an index in this case. But the key point I want to make here is that the cardinality estimate is now spot on. All right. Now, just some general recommendations to finish up. All right. Stats, really critical. All right. And you want them to be relatively accurate and relatively up to date. They don't have to be perfect. In many cases, close enough is good enough, but sometimes close enough is not good enough. You get these edge cases, okay? So you got to be wary of that, all right? My recommendation from 12C, all things being equal, would be to use the default values for method opt and estimate percent. And the reason I say that is I find in most cases where people try to do these things manually, a lot of cases, people just get it wrong. So all things being equal, I would recommend just using default values. Having said that, they're not perfect, all right? So there are still going to be cases where, ouch, I have to do some further investigation. But that is my default setting if all things being equal. Table cache blocks need to be changed from default of 1, all right? Set it to 42, probably set it to 16 would be the safest value. All right. It's just it mimics how ASSM does its free list maintenance, what used to be free list, how the number of blocks that Oracle will try to avoid for contention. It's much better than 1. Strongly recommend doing that. You will find you'll have much more accurate clustering factors. I haven't discussed it because I had to peel it out because I'm running out of time. So I'm trying to do it within the 90 minutes. But there is a new feature, which is quite nice, which is CBO Stats Advisor, which gives you advice on if you're not an Exadata, well, you know, these are stale, these are out of date, these probably should have had a histogram. Get familiar with that if you're not in an Exadata. Consider pending statistics, meaning rather than if you do collect statistics, rather than simply just publish them, and you've got that Monday blues where you come in on a Monday morning because you collect the stats on the Sunday and all things blow up, consider pending them first. But pending is only as useful as your testing. And with many, many scenarios and cases and customers I go to, they don't have proper tests. So you can't really do this properly anyway. But if you do have good testing, you can test your applications, then why not also test the impact of changing your stats? That's always a good if you've got good testing regime. And if things go desperately wrong on a Monday and you're finding that's often the statistics, learn how to restore stats to the way they were prior to your last collection. That is often you get out of jail card for things like where I discussed, you know, where we had that new outlier. Let's go back to where we were before and let's see what the issue is. And my final point is with indexes specifically, avoid using validate structure, even though it's often mentioned in textbooks and things, and it's just not what you want to do in current databases because of the lock-in implications. So just avoid validate structure of indexes. All right. I thank you. I've got 1 minute to spare. I have no idea how to handle questions because I'm not too sure how any of this stuff works. Oh, I've got one.
Problem. Richard,
Yes.
I'm here
Yes.
with one question. You
Yes.
have one question from Bhavani. Sometimes I see the misestimation in the join conditions. Is creating the histogram on join columns is a good option?
It may not help you with doing the joins, because what happens is you can get good selectivity on that particular table, but what Oracle struggles with is what is the outcome after you do the join on your join columns. And the problem is because you're not using the join columns to do your filtering, Oracle can't get the estimate easily. Okay, so this is where things such as dynamic statistics can be very useful, because it learns on the fly what the outcomes are of those join conditions and get you better estimates. So that's precisely one of the conditions for dynamic statistics, is to cater for that in that scenario.
Fantastic. We have another question.
Yep.
How the statistics are affected by Resource Manager? The point is that COB statistics are heavily dependent based in CPU. But if I limit with Resource Manager, like in using limit, how does it affect?
Well, if you've got your sys session, what you want to do is you don't want to have Resource Manager impacting your statistics gathering. All right, so whatever user activity that is doing your stats gathering, you don't want that to be impacted by Resource Manager, because you only have your window of opportunity to do this, and you normally pick a quiet time to do that. So you want to ensure that Resource Managers does not impact stats collection. I've just got my little question answer thing. E-rows is arrived by looking at column or distinct keys. So estimated rows is looked at by Oracle using the logic that I covered in that first third of my presentation. So what it says is, what percentage of rows do I think I need to use? And it will use the most accurate statistics that it can. If it can use distinct keys in stats, it will use that. If it can't, it will just use the histogram information or the basic 1 divided by the NDV. So it uses the techniques that I discussed in the first third of my presentation. All right.
Sounds great, Richard. Looks like no more questions.
Good.
Everyone, Yeah, everyone can remind, I just want to remind everyone that the replay session of this presentation will be available in a couple hours. That means that you can revisit this session as many times you want on the webinar platform, in the conference platform. And you can also interact with Richard by placing questions, comments, posts, and he will receive a notification every time that happens. And of course, Richard can reply on his convenience.
And if after that, was what happens is for the 2 weeks, people remember, and then a month later, people go, oh, bugger, there was this, I wish I knew the answer to this question. Here's my email address. So if you want to send me an email with a question, I encourage, questions are great because that way I learn myself. So don't be afraid to contact me on this email, post this opportunity for any subsequent questions, or post comments on my blog. That's another way you can get me as well. I hope you've enjoyed it. Hope you got some value out of it, and I hope you enjoy the rest of the virtual seminars. Thank you very much, guys. Thank you.
Richard, sorry, one more thing.
Yes.
Because I made you the host, can you please end the webinar to everyone? You are the only one who can do that now.
I've stopped the shared. Done.
Thank you so much. And now end the webinar. In the webinar option, you have